As chemists, we might be interested in the study of matter. Matter is simply stuff. So, when we define matter, what we're really talking about is stuff in general. It's anything that's tangible, anything that we can touch or interact with must be made up of matter. The only thing that we experience on a daily basis that isn't made up of chemical substances is light. Virtually everything else that we ever consider or interact with is a direct result of matter made up of chemical substances. Matter exists in all sorts of shapes and forms and sizes and levels of complexity. As chemists, we try to understand from the most fundamental aspect of material why it behaves the way it does. I like to show an introductory video or demonstration that reflects the scale of the universe. So let's do that here. In this video, we start with a depiction of something on the length scale that you're using right now, a screen. As we zoom out farther and farther, we find things that might be familiar, albeit odd, like T-Rex and a Japanese spider crab. Zooming out farther, and we see man-made and natural features. Farther and farther, and eventually we get to entire geographical features, states, or even small planets. Continuing to zoom out, we see even a Minecraft world over here. More stars, and eventually galaxies. Zoom out far enough, and we're able to see the entirety of the observable universe, which is approximately 10 to the 27 meters across. Everything that we know is contained within here. And if we zoom all the way back in, we can see that these vast things begin with tiny building blocks, like viruses, part of the reason that we're stuck doing this video demonstration. Individual particles or wavelengths of light, the building blocks for the electronic device that you're watching this video on, are DNA strands that make up life, molecules that make up individual cells like phospholipids. And zooming in farther and farther, eventually we get to the building blocks of those substances, individual molecules and atoms. These molecules and atoms are themselves made up of even smaller still components, subatomic particles. As we continue to zoom in, eventually we start to see some of those subatomic particles, nuclei made up of protons and neutrons, and surrounded by electrons. As we continue to zoom farther and farther, we get to theoretical extents, particles that are proposed on the basis of our physical approximation of what the universe must be built of. But at these small length scales, we go beyond what we really are able to do with the mathematics required in this course. We're going to focus on these things, protons, neutrons, and electrons, as the building blocks for matter and everything else that populates the universe around us. If we're going to be studying matter in this chapter, then we'd better have some terminology to be able to commonly refer to components of matter. We classify matter on the basis of the chemical substance or substances that matter is composed of. For a particular type of matter that consists of only one type of chemical, we refer to that substance as a pure one. Pure substances only contain one type of chemical. For example, pure water consists of only H2O and no other contaminants or mixes. As soon as we add something that's not H2O to water, maybe salt, then we've got a combination of two or more different chemical substances. This is the much more common form that matter takes on, a mixture. Of these two things, either pure substance or mixture, by far the more simple is a pure substance. In a pure substance, a pure chemical, all by itself, may either consist of an individual element or compounds, which are elements that have combined together in a chemical way. Elements are the smallest unit of matter that retain the same properties as bulk materials, so that when they exist on an individual small scale, they behave the same way as when they exist on an agglomerate large scale. Atoms are individual discrete components of the elements. Different atoms may belong to the same element or may come from different elements. Compounds, though, are always the result of two or more different types of individual elements binding together through chemical means. An example of an element could be oxygen. Or hydrogen. An example of a compound is water. Water results from two hydrogen atoms getting together with an oxygen atom, and all three atoms participating in a chemical bond. These atoms were first proposed through Dalton's atomic theory, which forms the basis for our modern understanding of what an atom is. All elements are made up in their smallest indivisible component form of substances that we refer to as atoms. Like the smallest brick in a set of Legos, an atom makes up the basis for more complex material. According to Dalton's atomic theory, of which there are 4 postulates, number 1 says that all matter consists of atoms at its most fundamental scale. Individual atoms are unique and cannot be converted from one type to another spontaneously. Atoms of one type share common traits and properties. We call this type of atom an element. Postulate 3 says that atoms are neither created nor destroyed in chemical reactions. They might just alter or change how they are arranged and what other atoms they bond with. Postulate 4 says that compounds form from a specific set of ratios of combinations of different types of atoms, so that water, for instance, can only form when 2 hydrogens and 1 oxygen atom get together. Given this working theory for the nature of the makeup of matter, chemists in the 1800s could work towards designing scientific hypotheses that are needed to infer how these atoms behave and what their properties might be. On your Moodle page, directly underneath the link to this video, is a PDF copy of a periodic table of the elements. You should download that and make that available to yourself as you're going through the rest of the chapters this semester. The periodic table lays out all of the elements, and there are 118 named elements that we currently know exist or have synthetically prepared on Earth. These 118 named elements all have in common an abbreviation. Chemists are lazy, just like all the rest of us, and therefore we simplify the identification of these types of atoms as elements that get abbreviations that might not necessarily reflect their English names. These abbreviations, or symbols for individual elements, are listed in individual compartments across rows and through columns on the periodic table. Names like hydrogen, symbol H, the first element on the periodic table, seem reasonable. But for a substance like sodium with symbol Na, it doesn't seem that the abbreviation matches the English name. Na for sodium, well, this comes from the Latin word natrium. And you might be familiar, if you're from Wyoming, with Natrona County. Natrona County is a hot spot for trona, or sodium carbonate ore. The root word for sodium comes from Latin, and hence is where we get our chemical elements symbol from. A worksheet follows that helps introduce you to elements' names and symbols from the periodic table. I would encourage you, especially if you have never taken a chemistry course before, to fill out that worksheet and start to become familiar with different elements and their symbols for abbreviations. The atom itself is composed of 3 subatomic particles that form the building blocks for matter. Alone, these particles are unstable, but together they form the basis of an atom. These particles include protons and neutrons, which are collectively located at an atomic nucleus. That nucleus is surrounded by electrons. We're going to talk about the fundamental physical properties of these subatomic particles. So we're going to come up with a table that lists a subatomic particle, its relative charge, and its relative mass. So here's our table. We've got protons, or P plus for shorthand, neutrons, or N0, and electrons, or E minus. Protons are located at the atomic nucleus. Neutrons are as well. Electrons exist in orbit around the nucleus, in things that are well described as clouds. The relative mass of the proton is 1 compared to the mass of the neutron and the electron. And the relative mass of the neutron is likewise 1. On a relative scale, protons and neutrons have effectively the same arbitrary mass. But in comparison, an electron is so small, almost 2,000 times smaller than a proton or a neutron, that its mass is effectively negligible. We can say that compared to a proton or a neutron, electrons have virtually 0 mass. As far as charge is concerned, these symbols help us identify the charges of these subatomic particles. The relative charge of a proton is +1. A neutron, like its name suggests, has 0 charge, and the charge on an electron is -1. Electrons and protons have the same magnitude charge, it's just that their charges are opposite in sign. Therefore, protons and electrons attract each other. Protons and neutrons contribute mass. Protons and electrons contribute charge. On the following slides from your Moodle page, you'll find some videos that show you how these subatomic particles were discovered. You should watch those videos and know that there are 3 key experiments that lead to the discovery of these subatomic particles. The first leads to the discovery of the electron through J.J. Thomson's cathode ray tube experiment. The next key experiment that leads to a discovery about the nature of these subatomic particles measures the charge of an electron for the first time. In this Millikan's oil drop experiment, charged particles are attached to oil droplets, and the magnitude of the charge on an electron in absolute charge is determined. Lastly, protons are discovered in Rutherford's gold foil experiment. In this experiment, atoms of helium stripped of electrons are projected towards a gold sheet. Occasionally, some of these atoms are repelled by virtue of positive charges that must reside at nuclei, dense clusters of positive charge, presumed at the center of the atom. Rutherford's work would go on to discover evidence of the neutron 2 decades later, and thus our total picture of the structure of an atom is less than a century old. Our modern depiction of what an atom looks like is shown here. An atom consists of a dense center of positive charge with protons and neutrons making up an atomic nucleus that's got a diameter on average of approximately 10 to the minus 14 meters across. This nucleus is surrounded by a cloud of electrons of negative charge. And this cloud of electrons is so large compared to our nucleus, 4 orders of magnitude or 10,000 times larger across, that most of our atom is just empty space devoid of anything, no particles whatsoever. Electrons are distributed throughout this diffuse cloud. The elements of the periodic table are arranged in a very purposeful order according to their atomic numbers. The atomic number, which itself is abbreviated capital Z, is indicated on the periodic table in association with a particular type of atom. For example, the element gold has atomic number 79. The periodic table is organized in order of atomic number, so that the very first element on the periodic table is atomic number 1, the next element after is atomic number 2, and so on. This atomic number comes exclusively from the number of protons that an element's atom's nucleus contain. The number of protons and the number of protons alone specifies the atomic number of an element. Therefore, we can always look to the periodic table and find the atomic number associated with an element to identify how many protons that element's atoms contain. Anytime we vary the number of protons, we fundamentally change the identity of an element. For example, hydrogen, because it's atomic number 1, always has a nucleus that contains 1 proton. As soon as we change the number of protons, we change the identity of an element. If we change the number of protons to 2 in the nucleus of an atom, we'd be dealing with helium. Helium always contains 2 protons. If we changed that number to 26, we'd suddenly be dealing with iron. If we changed that number to 79, gold. If we know the identity of an element, then we can use the periodic table to tell us immediately how many protons the atoms of that element contain. By default, elements on the periodic table are electrically neutral, meaning they have no net charge. Because protons are positively charged, to have no net charge, an electrically neutral element must have an equivalent number of protons and electrons. Remember, protons are positively charged things. electrons are negatively charged things. If we have an equivalent number of protons and electrons, we have the same number of positive charges as negative charges, and those charges cancel each other out, making a net charge equal to 0. By default, all elements listed on the periodic table are assumed electrically neutral. Neutrons, however, are not as easily identified just from the periodic table's list. Neutrons do not contribute charge to an atom, but they do contribute mass. Therefore, another quantity reflected on the periodic table can be used to infer something about the number of neutrons, though this inference isn't always direct. Instead, this mass that's reported on the periodic table is an average mass. It comes from all variations that naturally occur on Earth of a particular element. So the next thing that we've got to do is understand what those variations are and how they give rise to an average mass rather than just a simple, straightforward mass.